Consider the group Z6. Z6 consists of the integers 0, 1, 2, 3, 4, and 5. And the binary operation is addition modulo 6. So, for example, if we wanted to compute 4 plus 5, normally you would say 4 plus 5 is 9, but 9 mod 6 is the same thing as 3. Here's the group table for Z6, and we can confirm that 4 plus 5 is indeed 3. And I want to look at all the cyclic subgroups of Z6. So let's start by looking at the subgroup generated by the element 1. So if I look at this, I would start with 1, and then I would add 1 to that to get 2, and I could add 1 to that to get 3, and then 3 plus 1 is 4, and 4 plus 1 is 5. 5 plus 1 is 6, but 6 mod 6 is 0, and then 0 plus 1 is 1, and 1 plus 1 is 2, and then we're back to where we started. So this is the group that is generated by 1. Okay, let's look at the cyclic subgroup that's generated by the element 2. So in this case, I could start with 2, and then 2 plus 2 is 4, and 4 plus 2 is 6, but 6 mod 6 is 0, and then I'm back where I started. And how about the cyclic subgroup generated by 3? Okay, start with 3. 3 plus 3 is 6, but 6 mod 6 is 0, and so I'm back where I started. And how about 4? If I look at the subgroup generated by the element 4, I start with 4. 4 plus 4 is 8, but 8 mod 6 is 2. And 2 plus 4, that's going to be 6, but 6 mod 6 is 0, and so I'm back where I started. And how about 5? If I look at the cyclic subgroup generated by 5, I would start with 5. 5 plus 5 is 10, but 10 mod 6 is 4. 4 plus 5 is 9, but 9 mod 6 is 3. And then 3 plus 5 is 8, but 8 mod 6 is 2. 2 plus 5 is 7. 7 mod 6 gives me 1. And then 1 plus 5 is 6, and 6 mod 6 is 0, and I'm back where I started. And then finally I can look at the element 0. That's not very exciting, it just gives me 0. Okay, so what I want you to notice is that these two cyclic subgroups right here, these generate the entire group. In other words, if I look at all of the elements that are in there, they're the exact same as the elements that are in Z6. In other words, these guys generate the entire group of Z6. You can find the elements 0, 1, 2, 3, 4, and 5 in each of them. Okay, let's look at another example. How about the group S3? So S3 consists of the symmetry operations on an equilateral triangle. So if you remember that this row naught plays the role of the identity, the row 1 and row 2 things are the operations that rotate the triangle, and then the mu's are the flips across a line of symmetry. And the binary operation is composition of functions. That means doing two of these things in succession. And here's the group table for S3, and once again I want to look at the cyclic subgroups of S3. So let's start with, how about the identity? So that's row naught, and when you look at the identity, well, you just have row naught. Not very exciting. Let's look at the flips next. How about mu1? Okay, so mu1 and mu1 composed with mu1. Well, it's kind of flipping and flipping back. We expect to have the identity. And if you look here, mu1 and mu1, yep, that's the identity. And then it would make sense that the same kind of thing would happen for mu2 and mu3. We would expect to have mu2 and then the identity. And then same thing with mu3. We would have mu3 and the identity. Okay, what about the rotations? So for the rotations, I'll look at row 1 first, and then row 1 composed with row 1. If we look at the group table, row 1 and row 1, that gives me row 2. So I have row 2, and then when I compose that with row 1 and row 2 gives me back the identity. And then a similar thing happens with row 2. If you look at row 2 composed with row 2, you start to notice that we're going to generate the same thing here. We're going to have row 1, and then row 1 composed with row 2. That gives me back the identity. And if you notice, none of these cyclic subgroups are the entire group S3. In other words, no single element is generating the entire group here. So we saw that Z6 was generated by the elements 1 and 5, and we have a name for a group like that. We call it cyclic. While S3, we saw that no single element generated the entire group. That's not cyclic. So what is something that is cyclic? Well, a group is cyclic if it contains an element such that the cyclic subgroup formed by that element is the entire group. That's not a very precise definition. Let's make it a little more precise. A group G is cyclic if there exists an element A in the group such that G equals the group generated by that element A. And in fact, we can also say what a generator is. A generator of a group G is an element A in G such that G equals all those powers of A for A to the n, where n is any integer. And this is multiplicative notation. If I wanted to rewrite this using additive notation, I could say instead that I have A equaling, instead of A to the n, I would have n times A for any integer n. So this is additive notation. Okay, and so we see that Z6 is cyclic with generators 1 and 5, while S3 is not cyclic. Okay, so here's the definition of a cyclic group, and here's the definition of a generator. And we saw that Z6 is cyclic since 1 and 5 generated Z6, but what about Z7? Z7 is the set consisting of the integers 0, 1, 2, 3, 4, 5, and 6, and the binary operation this time is addition modulo 7. Here's the group table for Z7, and let's look at some cyclic subgroups. So we know that 0 is probably not going to be that exciting. How about 1? So if we look at the group generated by 1, we see that we would have 1, and then 1 plus 1 is 2, and 2 plus 1 is 3, and so on, and we would end up getting the entire group here. So that does seem to work here. But what about, I don't know, how about 4? Would 4 work? Okay, so we could try 4. 4, and then 4 plus 4 is 8. 8 mod 7 is 1. 1 plus 4 is 5. That's okay. 5 plus 4 is 9, but 9 mod 7 is 2. 2 plus 4 is 6, okay. And then 6 plus 4 is 10. 10 mod 7 is 3. And 3 plus 4 is 7. And 7 mod 7 is 0. So that worked too. And I'll leave it to you to check, but if you try any of the other numbers other than 0 here, and try and generate the cyclic subgroup from that element, you'll see that it does indeed generate the entire group. And in fact, for any integer n greater than 1, we see that z sub n is generated by 1 and also n minus 1. So this right here, that it's generated by 1, that kind of makes sense because you do 1 plus 1 plus 1 each time and you generate the entire group. This might not be so obvious that we have n minus 1 here. And later on, we'll look at a way of figuring out which elements of z sub n will actually generate the entire group. Okay, so other examples of cyclic groups. Z. So Z is just the set of integers and the binary operation is addition. And we see that Z is generated by the element 1. And 2Z, those would be things like negative 4 and negative 2 and 0 and 2 and 4. That's generated by 2. And 3Z, that's generated by 3. And I think you see the pattern here. NZ is generated by n. And so we need to make sure we have n, of course, greater than or equal to 1. Now, cyclic groups can be finite or infinite. We saw some finite cyclic groups when we looked at something like Z6 or Z7, and we see some infinite cyclic groups here when we look at Z and 2Z and 3Z. But what about cyclic groups that are abelian, or abelian groups that are cyclic? Are all cyclic groups abelian, or are all abelian groups cyclic? That's something we'll look at in another video.